Good evening, everyone. My name is Nathan Arnold, and today we're going to be going over my Teach the Doc for Chapter 9. So this chapter is covering gases. So for the first question, we had a conversion table. So we were given 680 millimeters of mercury, and we had to sort of convert that over to kPa, kilopascals, torr, and atmosphere. So we know that 1 kilopascal is equal to 7.50062 millimeters of mercury, and so therefore we are able to divide that by the 7.50062 to get the 90.66 with the unit above it. Here we know that it's a 1 for 1 with torr in millimeters of mercury, so therefore it's 680. For atmosphere, it is 1 atmosphere is equal to 760 millimeters of mercury, so we divide the 680 divided by 760 to get the number of atmospheres. For this first question the second question, the first question on the gas laws, we have suppose a gas has an initial pressure of 2 atmospheres. What happens to the pressure if the volume is doubled? Assuming temperature hasn't changed and mole of gas remains unchanged. So for this, we look at P1 times V1 equals P2 times V2. We're looking at this gas law. We know that the given here is that P1 is equal to 2 atmospheres. V1, we're just going to have BV1, the initial volume, and volume 2, we know that the volume is doubling, so volume 2 will be 2 times V1. And we go ahead and plug those known values into our equation, and we get 2 atmospheres times V1 is equal to pressure 2 times 2V1. And then we get P, or the second pressure is 2 atmosphere times V1 over 2 V1. And the V1s cancel out, so therefore we get 1 atmosphere. And for the second question, similar principle of finding the knowns and plugging them into our gas laws equations. So this one we're doing V1 over N1, where N1 is the initial number of moles, and V2 over N2, where N2 is the second number of moles. So here we have givens are 1.5 liters of initial volume, and then initial moles is just N, and then the secondary moles is tripled, so 3N. We go ahead and plug those into our equations. We're able to solve to get V2 is equal to 1.5 liters times 3N over N. The N's canceled, therefore we get 4.5 liters. Then, didn't write my name here, whoops. Then we go on to question 4, where we have PV equals nRT for the ideal gas law. We go ahead and write our givens, which is 1.5 liters for the volume. Temperature is given at 25 degrees Celsius, which you add that 273 to get it to Kelvin, so it's 298. And then pressure, we have millimeters of mercury, which we want to atmosphere, so we divide it by that 760 as we did earlier. And we go ahead and just plug into our given equation and solve. So we have all of our givens surrounded by N, and we will just have N be on this side and divide our value on this side by the R times the temperature, which R is the given value of 0.0821 liters or atmospheres times liters over moles per kilogram or Kelvin. And for number 5, we have similar principle again. We for this one, because this one's just going to be standard temperature, which is 273 degrees Kelvin, and then we go ahead and find the volume with the pressure of 1 atmosphere, and so then we go ahead and we find 1 times volume is equal to the givens that we have, and we calculate that out to be 1.34. Then we go to the equation that relates the density of a gas to its molar mass, and that equation will be derived from PV equals nRT, which we get, which we can then convert to molar mass is equal to the density times R times T over pressure. And so we're able to go to question 7 then and use this equation that we derived in question 6 and find the givens of the temperature and the density, and are then able to find the molar mass. So we plug in our givens, where R is always that constant, and the pressure is at the 1 atmosphere, and so therefore we get 20.18. We go down to question 8 here, where we're looking at the partial pressures, and so the partial pressure is the mole fraction times the total pressure, or compared to the total pressure. So here we have mole fraction of H2, where it's, first, my work's a little everywhere. First I calculated the total pressure of the system, or the total moles of the system, which is 1.47. So over here you go, mole fraction of H2 is the 0.5 divided by the total system, which is 0.34. The O2 is the 0.49 over the total system, 1.47, get 0.33. And then you do that for the 0.48 times the 1.47, or divided by, you get 0.326. So therefore H2 has the highest partial pressure. And then here we know that PV equals nRT, and then from that we can derive the P equals nRT over V, and that we are able to tell that P and N are directly proportional. So therefore the question with the highest number of moles, or largest N number, will be the largest pressure. So therefore we add them all up. We got 1.5 for A, 1.4 for C, and then 1.4 for B, and 1.6 for C. So therefore our answer is C. And go into question 10. Make sure you can see all of it. And we have a 25-liter cylinder, contains 3 grams of hydrogen gas and 14 grams of nitrogen gas, 25 degrees Celsius, which is 298 degrees Kelvin, calculated it here. Excuse me. So here we do the mole fraction, so we know the total, it will be the 3 grams over 2 grams per mole, so therefore it's a 1.5 mole. Mole of nitrogen gas is the 14 grams over the 28 grams per mole, which is half a mole there, and therefore we can do the overall mole fraction of H2 and nitrogen, which will be the individuals divided by the whole, so it's 1.5 divided by the 1.5 plus 0.5, which is 2, so you get 0.75 here, and do the same thing over here for nitrogen respectively. We do the 0.5 divided by the 1.5 plus 0.5, which gets you 0.25. Oh yes, here I did the total mole. And then for the partial pressure of each gas, we'll go ahead and go back to our PV equals nRT. And we're solving for P, so we have P equals nRT over V, where R is a constant. T was given to us above, which we found to be 298. And then 25 liters, the volume was given as well. And so therefore, and also we solved for N in part A, the 2 moles. And so therefore we were able to solve for the pressure overall, which is the 1.96 atmospheres, and then multiply that times the partial pressure to find the partial pressure for each gas specifically, which is the 1.47 atmospheres for hydrogen and 0.49 for the nitrogen. Thank you very much for watching. I hope you're able to learn something from this. Yeah, I hope you have a wonderful day.